My name is Fabian, and I have now the very personal pleasure to introduce to you my highly estimated colleague, Dr. Florian Schepers. So, just as a quick reminder, this today is still TNG Big Tech Day, and naturally, at Big Tech Day, we would like to shine with our brightest and most impressive personas. So let me give you quickly 3 reasons why Florian, from this perspective, is the obvious choice to give such a talk today. First reason, Florian has a PhD in physics. Well, not just any PhD in physics, because that would be TNG standard. No, and I have to read this. Florian has a PhD in physics, where he worked in the area of nonlinear waveguides and laser development and led a team for transverse modes in solid-state lasers. So I asked GPT, and GPT and me agreed that for me, a proper definition would be Florian did pretty cool laser stuff during his PhD. Second reason, Florian is a passionate problem solver, and he has been proven to do so since he joined TNG in 2021, where he's working as a senior software consultant. And he doesn't just solve problems. No, sir, he solves problems that actually matter. For example, the problem of writing down meeting minutes, and if that would be solved, would be great, and he will tell us today how. And third reason why he's the best candidate for speaker today is he solves those problems by using state-of-the-art AI tools, and that all in an open source flavor. This runs by the name of Meminto, which we will show us today. So if those 3 reasons did not get you excited for our next speaker, frankly, you came to the wrong place today. So please give a very, very warm welcome to my colleague, Dr. Florian Schepers.
Yeah, thank you very much, Fabian, for this really nice introduction, and welcome everybody to this talk, where I want to take you from the idea to the implementation of an AI-powered meeting minute tool. And when I sat down to design this talk, I thought I wanted to do it in a bit more hands-on approach, so that hopefully after the talk, most of you will feel confident to build such a tool themselves. But before we go into the technical details, I would like to start with some motivation how I actually came to work on this project. So when I started at TNG, I quickly learned that there's quite a steep learning curve in IT. I mean, I was a side entrance, and the advantage that we have on our side here is that we have quite knowledgeable and well-expertised colleagues that we can ask for advice and that can help us to develop ourselves further. And in my particular case, that was one colleague who gave me a really good advice that I would like to share here. And that is, if you want to become good at a certain topic, find something you're passionate about and start building something from scratch. By doing so, you will have to deal with all the different technologies that you want to use here. And you will be the one who has to live with all the different decisions that you made during the way, which will be very valuable lessons. At that point, I was really hyped to find something to work on, but I still had the open question, what could be my project that I could work on? And then something happened. There was suddenly a disruption in our field with the rise of AI. So suddenly there was a new technology that started to change the way how we are working. I would say, particularly with the release of ChatGPT 3.5, it really started to have a heavy impact on our work. And this made me really curious, and I was thrilled and threatened at the same time. Thrilled because due to the vast opportunities that we have due to these tools. So they were promising a lot what they should be able to achieve in the future. So that was really exciting, but also thrilled because I just started a new job in IT, and suddenly there's a tool that promises to someday might even replace software developers. So I saw for me 2 different options. Either I could stick my head into the sand and hope that I will get through somehow, or I can start to embrace AI and try to use the different tools to get ahead. And obviously I decided for the latter one. So if we talk about productivity, what we can use these AI tools for also, there's one additional point, and that is that I learned that working, especially remotely, can be very distracting. So you have a lot of distraction that you have during your work. So might it be emails that are incoming, or maybe Slack messages, And actually, in contrast to computers, we are not so well designed to handle problems in parallel, but are more or better suited to do one thing at a time and do it sequentially. And one thing where this annoyed me in particular was during meetings to take meeting minutes, because I had the feeling I could either concentrate on the meeting and really participate to the meeting, contribute to the discussion, or I could concentrate on taking my meeting minutes, have good meeting minutes at the end, but then I would lack to participate in the meeting. So I wanted to have my own project. I wanted to do something with AI, and I was really annoyed by taking my own meeting minutes. So the path for me was quite obvious. I wanted to design my own AI-based meeting minute tool. And with this, the Meminto was born, the meeting minute tool, where I used different AI tools to transcribe and summarize my meetings. And this then should free me from actually taking those notes for myself. But I had a couple of requirements that I wanted to be fulfilled. And the first one is that I wanted it to be open source, so that I could share it with the community, and also people could use it for their own uses and might even contribute to it. Then the second was that I wanted to ensure data sovereignty. So I'm working in consulting. We are having a lot of topics that might be confidential, and therefore I wanted the user to always have full control over his data so that it's not leaked outside of the context. And finally, I wanted it to work out of the box. So I wanted to use tools that just work right out of the box. I didn't want to start to train my own models or to do some fine-tuning, but yeah, just get started. So the idea is clear. I want to have some audio recording of my meeting. I can just do it, for example, in a remote meeting using Zoom or Slack, Zoom or Teams to record my meeting. And then I take this audio file and want now to somehow get the meeting minutes out of this. And we now will take a look how this process works, that we get the meeting minutes out for this. And I basically used 3 different AI tools to achieve this goal that we'll go through now step by step. The first issue we'll have if you have such an audio recording is that there are multiple speakers in a meeting. So there are a lot of people, might even interrupt each other, and you have to identify which person said what, because it can have a significant impact on the meaning of something that was said. So the first thing that we have to solve is the so-called speaker diarization. So speaker diarization means you have like your audio track, like this schematic that you can see here, and you now want to segment it into the different parts that were spoken by different people in the meeting. And in this particular case, we also, or in general, we do not only want to identify the different speaker segments, but also we want to identify which segments actually belong to the same speaker, so that we can see who is actively speaking in this meeting and what they said. So in this case, for example, that we identify that the first segment and the last segment both were mentioned by speaker 1. In order to achieve this, I used the tool pyannote.audio, which is an open source toolkit written in Python. So that's already great. It's open source. It fulfills our first requirement. Then it's based on the PyTorch library and provides a set of trainable end-to-end neural network blocks that you can then stick together in order to build such a speaker diarization pipeline, as you can see on the bottom. And the nice thing is that the developers from pyannote.audio provide us already with pre-trained models that we can just reuse right out of the box. And finally, you can run it locally on your machine so that you have full control over your data. In my particular case, I had to use my CPU and had a real-time factor of about 1. This means for 10 minutes of audio that you want to diarize, you need about 10 minutes diarization time. But if you have a computer with a CUDA-capable GPU, for example, you can get way better results, going down to a few % of real-time factor. So a real-time diarization is very well possible. So let's now take a look how the process works internally. First, we have the audio trace of our meeting, and then pyannote.audio does a feature extraction. So this basically means that we need to bring our audio trace into a format that's such that the subsequent models can actually use it and work with it. And in our case, this is a so-called spectrogram, where we have on the x-axis the time domain, and on the y-axis the frequency, while the amplitudes are color-coded. From this spectrogram, we can then, in the first step, do a so-called speech activity detection. So this is basically just identifying those sections of the audio recording where somebody at all is saying something, so that we identified all the interesting sections in our meeting. In the next step, pyannote.audio then tries to identify speaker changes. So maybe I'm saying something, somebody else is interrupting me, then it's one segment of speech activity, but the speaker has changed, and I need to identify this speaker change. And this is done by this third module. And then finally, I have all the different segments that were spoken or actively spoken by different persons. And in order to now identify which of these segments belong to each other, I need a so-called user embedding. So I find a vector representation that kind of captures the tonation and the way something was expressed, so that I can identify which of these segments belong to the same speaker and which belong to other speakers. And with this, I can then build this cluster cloud, group it, identify the different speakers, and finally come to my final speaker diarization, where I can identify which segments were spoken by which person. So, as I mentioned earlier, I wanted to do it in a bit more hands-on approach. So let's now take a brief look how this can be implemented in the code. And therefore, I will bring my VS Code to the screen. Just give me a second. I will zoom in a bit because the screen is not so big. But yeah, I wanted basically to convey that this is a quite simple, simple thing to do, because pyannote.audio does already do all the heavy lifting for us. We only need to import the... Okay, I don't use this. Pyannote.audio, we basically just need to import the pipeline from pyannote.audio. We can then define a diarizer that we need to initialize with some model that we want to use, provided by pyannote.audio, a Hugging Face access token, in order to download it. And then we can just create a function, diarize audio, that takes the audio source as an input. Then we define the pipeline to actually run the diarization, and just provide it with the audio file. And this will then return the diarization for us, and we can return it to the user. So you really need, see, there's not a lot of complicated logic in here in order to use this tool. So let's go back to the slides. And with this, we already accomplished our first step. We now have a diarization and understand at which time which person is saying something. Now, in the next step, we have to understand what they are actually saying. And for this, we need a transcription of the spoken text. And for this, we first take our audio file, split it into the different speaker segments that we got from pyannote.audio, and then for each of these sections, we will calculate the transcription based on the audio section, in order finally to kind of merge all these transcripts together and generate one final set of transcript. And in order to do this, I used Whisper from OpenAI, which is, again, open source toolkit under the MIT license. It runs locally, again, with a real-time factor of about 1. So if you use a CPU, but you can come down to a few %. It's typically also, in many cases, used for actual subtitles that you can see during many meetings. And finally, OpenAI provides multiple different models of different size that we can use for our tool here. So that's also really great. Whisper itself was trained with about 680,000 hours of audio files, and it can actually do multiple things. So first, it can do English transcription, so just transcribing in English. Then it can transcribe like any text spoken in like many different languages, and then transcribe that to English. And finally, it can also do the transcription in any other language, for example, from German to German. And yeah, of course, it can do non-speech detection, which is also important. The audio file is then again represented in a way so that the computer can handle it well in the form of such a spectrogram where we have the time domain on the x-axis and the frequency domain on the y-axis and color-coded the different amplitudes. And this is called a log-mel spectrogram because the amplitudes are actually in a logarithmic scale. So I guess you know it if you go to your CD player, for example, and turn the volume. It's typically done in a dB scale because it's a logarithmic scale. And also for the frequency, we have a so-called Mel curve that basically represents how we perceive different frequencies, and therefore also the frequency scale here was corrected by this Mel curve. We then take this spectrogram and feed it in a so-called transformer. So, of course, I didn't do this, but Whisper, when they built the Whisper transformer, did this. And such a transformer is really a breakthrough. So when this came out, it enabled to actually train these AI models on a parallel fashion so that we can use much more training data during training, which resulted in way better models that we could achieve. And we will go through this. The idea here is to go through all the different components and at least understand what their task is. But we will not go into the details how such a transformer actually works and accomplishes the different goals. But if you are interested to learn more about this, I can highly recommend to you the talk of Brand Sanderson later, where he will go into the different details and steps, how the actual data flow through such a transformer, especially for the decoder part, will be. So for now, we can take a look at this transformer. On the left-hand side, we have the encoder block. What processes actually our audio file that we give as an input. And on the right-hand side, we have then the decoder block, which is responsible for the generative part. For simplicity reasons, I will now consider a translation. It's quite similar to a transcription, but I can give way better examples. So this is why we now, for the moment, assume a translation instead of a transcription, but the idea is always the same. So the first step is that if we have some input text and we feed it into our system, we need to calculate a so-called embedding. As like a computer doesn't handle words so well, we need to find some numerical representation, for example, in this case, in form of a vector. The embedding then should not be just some vector for any word, but we want the embedding to carry some meaning. And basically, this means if we, for example, have the words cat and dog, they should be close to each other because they carry a similar meaning, while they should be far away in the vector space from words that carry a completely different meaning, like, for example, car or motorcycle. And note that this is even the case, even though the words car and cat are written quite similarly. So they use the same letters or quite similar letters, but still they should be far away from each other because we are concerned with the actual meaning of a word. We can then take this embedding and in the next step need to calculate the positional encoding. So the positional encoding is basically responsible so that we can understand the meaning of a sentence based on the position of the different words. If you, for example, have the sentence, the cat sits on the elephant, it's quite vital for the cat that it comes before the elephant, because if you turn it around, you will get the elephant sits on the cat, which is quite devastating for the cat. So this is why we need this positional encoding to understand where in the text our words are actually coming. From this, we can then go to our encoder blocks. So this is a chain of like kind of the same block one after another, and this does actually the heavy lifting of understanding what's going on in our text. And each of these blocks is made out of two parts, the self-attention block and the multi-layer perceptron block. So the self-attention block tries to understand the meaning of a word based on its surrounding. For example, if we have the word queen in the sentence, Elizabeth II was the Queen of England, based on Elizabeth II and of England, we understand that we are talking about the Queen in the royal sense. While if we have the sentence, I went to a Queen concert, we directly understand that we are talking about the Queen, about Queen as a band Queen. And therefore, you can see that the words and the surrounding can really have a heavy effect on the meaning of a word. And I like this example because you could also have the sentence, "The Queen went to a concert." And you see that this sentence is actually quite similar to the second sentence, but again, the meaning changed, and we are talking about the Queen in the royal sense. So in order to also kind of get these fine granularities, we need the multi-layer perceptron blocks. And these actually take the information from the self-attention blocks and refine and improve the informations from them. So if you ask ChatGPT to describe this in a more colorful way, it will tell you that the multi-layer perceptron blocks turn the rough sketch that you get from the attention blocks into a detailed painting by adding multiple layers of color. So I think this is quite a good description to understand what goes going on here. And with this, we now have completed the left-hand side and have a full encoding of our input text that we want to translate. And now we can take this whole encoding of our input text and feed it into our decoder block on the right-hand side. And here we can then actually do the generative part where we want to generate our translation. In order to do so, we have at the bottom some input sequence of tokens. In the beginning, this input sequence is basically empty. It just has some tokens at the beginning kind of that describes the task at hand. For example, you should translate, and you should translate it to English, for example. As I mentioned earlier, the tools can actually achieve different tasks, translating to different languages and so on. Then the next step is a learned positional encoding. Here the task is quite similar to the previous sinusoidal positional encoding, but the parameters of this encoding are learned, so they can change during the training process. And then we have our decoder blocks. And the decoder blocks are quite similar to the encoder blocks on the left-hand side, with one very important difference. We have these cross-attention blocks in them, which basically do the heavy lifting for us of doing the actual translation. So they kind of do the cross-connection between the different languages, in our case now, for example, German and English. And with this, we can then just generate the next most likeliest token, and by repeating this process over and over, we will generate a full transcription of, or in this case still, translation of our given text. And now, of course, we change the input back to the log-mail spectrogram, have to redo the training, of course, because before it was optimized for translation, now we want to have a transcription. And once we have done that, we can just generate the transcription of our input text and get the spoken words into a written form. So let's get back to the task at hand. We have our audio file. We split it into the different speaker segments, transcribe each of these segments using Whisper, and finally we'll generate the transcript out of this. And let's now take a look how this can be achieved in code. So for this, we will go to the transcriber. And again, we have to hand in some model. Whisper has different model sizes available, so we have to choose one. We can decide if we want to do English transcription only, or if we also want to support different languages. Then we will have to set up our transcriber by defining which model we want to use, whether we want to use a GPU or a CPU. This is basically decided if you have a CUDA-capable GPU on your computer or not. Then we will set up the Whisper processor and model itself, and then can basically define our pipeline that we need to run the transcription. Then we have here a function that's called like just transcribe, and as an input, this simply gets the audio sections that we obtained by our diarization earlier, and then we can loop over all these different audio sections and always run our transcription pipeline on each of them to get out our transcript. This is then stored in some custom-made type that contains the start and the end time point of something that was said, the speaker who actually said it, and the text that was actually said during that section. And with this, we will again get out something like this, which contains a full transcription of our meeting with all the different speakers, with all the different timestamps when they said something, so that we have now the full information from the meeting in written form. Okay, and with this, we have made a very important step, because as it's now available in written form, we made the information kind of usable using large language models. And of course, I'm one step ahead. So we now have the full information as a text, and we need to generate now the final meeting minutes. And therefore, of course, we use large language models because they are really designed to handle large bodies of text very well and to generate our meeting minutes for us. And therefore, we need to define some instructions, basically something like, hey, you're a useful assistant, and your task is to take this transcript and generate meeting minutes out of this. Of course, a bit more elaborate if you want to get good results, but it basically covers the essential idea, what you need to instruct. Then you define your transcript, or take your transcript together with the instructions, feed it to the LLM, and it will generate the meeting minutes for you. And now we want to understand how such a LLM works. There are different architectures, mainly BERT from Google and GPT Transformer from OpenAI. And I would, in this talk, like to concentrate on the GPT Transformer architecture, which is probably a bit more popular. We want to start for that at something that we already know, which in our case would be the Whisper Transformer. But in this case, we already have like our input sequence here for the generative part, as this will be our instructions and the transcript that we generated earlier. And we do not have something like a spectrogram or like the text that we want to translate. Therefore, we kind of can get rid of this left side part of the encoder blocks, and therefore also from the cross-attention blocks in the decoder block. So with this, we can just simplify this. And let's also simplify the input and drop all these special tokens so that we just remain with our input sequence and want to get our output sequence out of this. Then we still have a learn positional encoding here for GPT transform architecture. We actually don't need that. We have a sinusoidal positional encoding. And also in the decoder blocks, there are some differences. So we have a masked self-attention. This basically means during training, you typically have large bodies of text that you put in and then let the LLM generate some prediction and compare it with the text that you would expect to come next. And in order to train the model correctly, you have to hide kind of the ongoing text from the LLM so that it cannot peek and see what will come next, but will have to make a guess in order to find out what will come next. Also, we use no longer multi-layer perceptron blocks, but fast-forward neural networks, which are very similar to multi-layer perceptron blocks, but have some more degrees of freedom. Also take as a note that this is a very simplified representation of a GPT transform architecture. Typically, you would have some linearization or layer normalization in front of the different layers, and also some linearization and softmax function at the end. But I think this is, for now, a good enough representation to understand what's going on here. And with this, now we can, again, repeatedly generate one token after the other until we have our desired output. And in our case, we feed just our instructions and our transcript in, and will then generate our meeting minutes as an output. As I mentioned earlier, I wanted the tool to be, it should run mostly local so that people have full control over their data. You actually can run LLMs locally using tools like, for example, OLlama or Llama CPP. Both run locally, both are published under open source license, and you have a lot of different models that you actually can use to run them and to generate your completion for you. But for Meminto, I chose to go a bit different route because I didn't want to ship, or I didn't want to expect the user to set up a whole LLM locally on his machine. So therefore, Meminto simply accepts an endpoint that he can call and can reach an LLM via this endpoint. And then he simply uses this LLM to generate the meeting minutes for you. And by doing this, the user has the free choice of selecting the model or the provider that he actually wants. So he could either use one of the tools that I showed earlier to run the LLM locally on your machine. Or if his company, for example, provides an LLM on-prem, he could simply use this. So for example, that's what I'm doing. TNG has a GPU cluster, runs multiple LLMs there, and then you can just use one of these LLMs to actually run the model. And then finally, we have, of course, third-party models, as for example, provided by OpenAI, in case you say, okay, actually the meeting was not that confidential, it's fine for me if the information is leaked, then you can use a tool like this. The nice thing here is that this really provides a good scalability in an environment where we have a very fast pace. So nearly every 2 or 3 weeks, there's a new model that's now the hottest model in the field, and you always want to use that. And as most of these models adhere to the same endpoint architecture, you can just use them interchangeably. And that's what I think really nice for this tool. So now let's take a look how this can be implemented in the code. To just call such an LLM. Therefore, we can go to our LLM here. And again, we just define our own class called LLM. It gets a model that you want to use, the URL where you can reach the model. You need some authentication, typically, so that the endpoint knows that you're allowed to actually use it. You need to set the temperature to define how creative the LLM should be, and you have to define the maximum token size that you can use to generate your response. Then you can simply run this infer method where you have some header that kind of gives the important information on how to communicate with the endpoint. So basically it contains some definition about the format of the body and also of the authentication. And then you need some parameters that are required for the inference. Mainly, it contains like the system prompt. In our case, this is just the instructions to the LLM. And our user prompt, in our case, this is the transcript that we hand in together with the instructions. Then you can just call the post endpoint, the endpoint with a post request, and this will then generate the response for you, which returns like the meeting minutes, hopefully in the content of the message body. And with this, we now achieved our goal. If we now take a look here, you can see that we now were able to really generate meeting minutes out of our initial audio recording. So here you can see that we defined, this was a fictional, or this was a discussion with my colleague where we talked about a fictional game and we wanted to design some high score board for this game. You can see that it correctly got the idea what we want to do. It correctly listed all the different decisions that we made during the meeting, and it also assigned the different tasks correctly to the participants, so we purposely define some tasks for each other. And finally, we have this section below here with additional notes where he kind of lists everything that didn't make it into the sections before, but might still be relevant for people that didn't participate in the meeting. So if they read it up, they can also see that these points were also discussed. And with this, we are basically done. So you could say we call it in early, but we have one issue still to solve, and that's basically the limited context size of our LLMs. So an LLM can only process a limited number of tokens at once, and this is defined during the training or fine-tuning of a model. So for a typical context size of GPT-4 Turbo, for example, you have around 128,000 tokens, and which is more at the upper end. And for Llama 3, you have like a limit of about 8,000 tokens. And to get a better idea what this means, we now can assume that we have a model that we trained with a context size of about 5. And if we now feed in the sentence, lunch is at the, we still have 1 token left that we can use for our prediction. And now it can predict, of course, anything. It can lunches at the restaurant, lunches at the cafeteria. As a good TNG model, it will, of course, predict lunches at the maze, because that's typically the place where we go for lunch during our tech days. But now let's assume that we have trained a model only with a context size of 4. And in that case, not all of our text fits into the context size of our model, because we always need one token left for the prediction itself. And then the same happens as with the coffee cup here on the right-hand side, and some of the information will be spilled. Typically what you do is you will cut the first tokens at the beginning, because they tend to have the least impact on the on what you want to generate. But as you can see here, it has a significant impact, as we will now drop the lunch, and the input will only be is at the. And these are three very generic words that do not make any sense to really predict something. You can just predict anything after that, and therefore the prediction will be useless. So what does this mean for our transcription? We have a very long transcript. Like the meeting went over time, we have a very long meeting. Then we need to chunk our transcript into different parts. And then we can generate meeting minutes for all of these different parts. And then one by one merge these meeting minutes together again until we have one final set of meeting minutes of the whole meeting. So let's take a look how we can implement that in the code. Therefore, we need to go back to the IDE, and we have the meeting minute generator, as I called it. It will get a tokenizer. It's basically required to calculate or to measure how many tokens the input text has. And we need an LLM to run the generation, of course. And then we can just run the generate function, which will first, in the first step, split the transcript and generate the meeting minutes for each of these different chunks. Therefore, we define some system prompt where we tell it, yeah, you're a useful assistant. Please generate meeting minutes for this transcript. And we can also provide a nice example so that he kind of has a format and knows how he should actually format his output. And then we simply run below here the inference with these instructions, and it will generate. First, of course, we need to chunk the transcript. So we give it to this function, and we'll cut it into decently sized pieces so that they will fit into the context size of our LLM. And finally, we can then loop over these transcript chunks and generate meeting minutes for each of these chunks. Then we hand these meeting minute chunks into our second function, which is called merge meeting minutes. And this will just take the meeting minutes and merge them one by one. Therefore, again, we will define some system prompt where we tell it, okay, you will now get multiple meeting minutes. Please merge them into one. And then we will loop over all these different meeting minutes. And I will spare you the complexity of this loop, but it will basically then generate the final meeting minutes for us. Okay, let's go back to the presentation. And the output will then look like something like here. And you can see this looks quite similar to what we had earlier. So it's the same meeting. It generated meeting minutes for us. But you also can see some differences. And the first one is it's much more verbose. So there are much more bullet points. And also you can see in the decision parts, you have like two sub-headlines, which are basically the same. You have the scoreboard and the leaderboard. So the meaning kind of is the same. So it could have merged these subheadings, but it didn't. And this is where I would say that there's still a shortcoming, that it sometimes doesn't manage to understand that like same bullet points or same subheadings have the same meaning and could be merged into one. So there's still room for improvement, but still we are now able to generate meeting minutes for meetings that can be indefinitely long, which is great from a technical perspective, but maybe not for all the different participants. With this, I would like to come close to the conclusion. So let's take an outlook where this journey could go in the future. So I already mentioned that this approach of generating meeting minutes for very long context sizes has its flaws. So I've thought of an alternative approach that I would like to implement next, which is basically generating the meeting minutes consecutively. So you take your transcript, you split it into the different parts, and then generate the meeting minutes for the first part, and then just kind of append the information that you get in the subsequent transcript parts. And what you also can see, which is really nice, is that we need way less calls of the LLM, and therefore we can reduce our costs. Also, what's really nice, this enables an alternative workflow where we have kind of the on-the-fly meeting minute generation, where the AI sits at the table together with us and listens for about 2 to 3 minutes, and then will generate the meeting minute into a shared file. And then you can directly read the meeting minutes that it has written so far. If you don't like it, you can modify or correct it. And during the next iteration step, it will then also consider these meeting minutes for the next meeting minute generation. And therefore, your changes will survive during this iteration circle. So this is kind of the vision where I would like this tool to go next. With this, we are kind of at the end, so I would like to summarize what for me personally, take away from this project. What are the fruits to harvest? So first, it was really great working on this tool because it helped me to expand my technical horizon. I didn't have the opportunity to work with any AI tools before, and now in this project I could do this. I also learned that most of these tools are really easy to use because they are very well documented. They have a vivid community with a lot of good tutorials that you can profit from. And a lot of tools also provided by bigger companies are actually open source, which is a great thing. And finally, it really helped me to expand my professional network, as a lot of people were interested in this tool, both in the IT field and also in the non-IT field. And I think that was really great. It gave opportunity to a lot of discussions that sparked kind of some new ideas on how to continue with this tool. And as these discussions sparked some good ideas for me, I hope this talk could help to spark some thoughts to you, what could be your next project that you could work on. With this, I would like to thank you for your attention, and I'm happy to answer any questions you might have.
Yes. Thank you, Florian. That was really inspiring. Do we have questions? Yes. Coming to you.
Well, thank you. I was wondering what kind of influence you have on the final output. Like, for instance, I don't want the next steps, or I don't want the things that are in the backlog or somebody should take care of. How would I structure the output? Thank you.
What do you mean with in the backlog?
Like for instance, there would be, or the first output would generate a section, a header. Okay, this is the backlog, and I have identified these 3 points that somebody said that should go into the backlog. But now for this kind of meeting that we don't have such a thing. So we would like to remove automatically everything where somebody said, okay, that should go into the backlog.
You mean some post-processing of the meeting minutes? Did I understand that correctly, or?
Well, not necessarily. It could also be like the prompt that generates the meeting minutes. Is the influence on the output only defined by the prompt that generates the meeting minutes?
I would say there are 2 parts that mainly contributing how your final meeting minutes would look like. And that is the instructions that you give to the LLM. So I say something, I want to have these sections, please provide them to me. And I also have something like this example that I gave, which kind of provides a template. And via these 2 degrees, you have the opportunity or the possibility to change that. So if you say, I didn't like the layout that Florian used, please, I will just give it in my own template. And maybe you have also some things where you would like to put a focus, what you want to have in your meeting minutes. Or, if I understood you correctly, something that you don't want to have in your meeting minutes, then you of course also state that during the instructions. But my personal experience is that I wouldn't overload the LLM with instructions in one step. So if it already generates the meeting minutes and you have thousands of different requirements, it might get messy and it might forget some things. So I would think about, rather than doing it one step, just add another step where you tell the LLM, for example, to filter everything out related to the backlog.
Thank you. Any further question here?
Yeah, thanks for the talk. This may be a little bit of follow-up question to that one. I mean, you have different kinds of meetings. So you have decision meetings, you have informational meetings. So this you would then cover with the instructions or the system prompt up front, or did you find out that anyhow the LLM will adapt, so to say, to the content and then structures the meeting minutes accordingly? Or
No, the LLM will adhere quite closely. Let me get it back. To the instruction that you gave it. And when we go to the instructions here, for example, or like these are the instructions that actually generate the meeting minutes. So let's take a look here. I purposely put those things into constants where you can just modify the prompt. So I have some file here that's called prompt.py, and then you have here, for example, the instructions. And if you don't like the instructions that I used because you should optimize it for your use case, you can just go here and modify them, and you actually do not have to touch the code at all. And the same is here, for example, with the example. I gave a brief example of a birthday party, like there's a surprise party to be organized. And if you don't like this setup, or you want, for example, to have some additional headlines or things like all the different participants that contributed or so, then you can just add it here, for example.
Do we have any questions from the streaming audience?
So there's one question from outside, which is a little bit the question about if you or how you or if you want to do it, how would you extend such a system that it could, for example, also match the information during the meeting to a timestamp that you can check it in a recording later, if that would be something feasible?
If it matches the information outside of the meeting?
And that it can give like timestamp information, okay, that was discussed at that time.
You mean like this decision was made at minute 5 or something like that?
Something like that. So that's how I would read
I mean,
the first part.
It's a bit tricky, but in the transcript of your course, you have the different timestamps. So theoretically, the LLM knows at which time point something was said, and if you adapt the instructions accordingly, you might be able to get the LLM actually to add the timestamps to the meeting minutes, especially if you, for example, add it to the example. So this is a common strategy to have few-shot prompting, and my experience was that this example that you give to it has a really strong influence what the LLM does or doesn't do. So if you would add here like some timestamps when the different things were said, I'm optimistic that the LLM would manage to extract these information from the actually given text. But I didn't test that, and so you would have to try it out. I'm happy for any contributions that go in this direction. Would be interesting to see.
All right. Maybe one really quick final question from my side. How could I use this at home with my, let's say, Zoom call?
So in Zoom, it's quite easy because you can just record your Zoom call, and then afterwards you will also directly generate an audio track of that, and then you can just call the script and lead it to the file where the file is living, and then you can run it. If you want to try out this tool, by the way, in real life, I will invite you to come to the AI showcases where you can, where this is running, and you can just record your own pseudo meeting and generate meeting minutes from that.
All right, so now we all know where to go next. Let's thank our speaker again, please.